Hello, everyone. It's noon, so I'm going to go ahead and get started. Hopefully you can all hear me. Hopefully you can all see me in front of the slides. So today I'm going to talk to you about the Masters in Scientific Computing and Data Analysis program here at Durham University. You might know this program as MISCADA, which is the acronym. I'll say MISCADA throughout the presentation. I'm going to do a quick overview of how the program works before talking a bit about some student testimonial and then giving you a taster of some content you might see on the course. So first things first, let's just meet the team. So the director of the MISCADA program is Dr. Anna Reinertz. She can't be with us today. She's at a conference. And me, that's Dr. Christopher Marcotte. I am the deputy director. So I'll just play this short video.
MISCADA is a suite of MSc courses made by scientists to train the next generation of scientists. For this, we have leading experts from the field. We equip people with the newest kit, and we run everything in brand new facilities.
So we've got an all-new math and computer science building since recently here in Durham. There's also a new teaching and learning center. Durham's a very old, very beautiful city. It's a World Heritage Site, and the university has a collegiate system. It has a very friendly, very international community of students, and it's a very, vibrant and rich city to live in.
MISCADA consists of three pieces. We have generic methodological training, we have a specialization area, and we have professional skills training.
In the general methodological part, the students will learn how to write large-scale software for simulations, as well as work with large data sets. We've got 4 specialization areas. We've got earth and environmental sciences, financial technology, astrophysics, and computer vision and robotics. In earth sciences, we focus on the prediction and analysis of phenomena behind climate change, natural hazards, and natural resource management.
In financial technology, we focus on the mathematical principles behind financial markets and cover a range of areas, including probability theory, statistics, and mathematical modeling, to name a few.
Our astrophysics specialists try to find out why we think the universe is mostly dark matter and dark energy. They use cosmological simulations and galaxy surveys. Plus, they use among the best computational kit available in the UK.
Our specialists in computer vision and robotics make machines understand the environment around them, allowing robots to operate and interact seamlessly and autonomously with the world around them. For this, they rely on cutting-edge artificial intelligence and sensing technologies and build machine learning systems which both learn from and adapt to their changing environment.
There's a lot of synergies, a lot of interlinking between the different modules, and you actually learn to utilize what you are learning in your courses.
So after the MISCADA course, a lot of the students go on to do PhDs. It's a very research-focused MSc. A lot of them also go into companies to work in research and development in those companies. They go into finance, they go into high-performance computing, all sorts of things.
The ideal student has a background in the specialization area already. It is important to have good math understanding and good programming skills, because we want our students to take the newest theoretical ideas and directly translate them into working codes in their respective application area. If you want to work on the highest level in your area, either in academia or in industry, then this is the right course for you.
Okay, so I think most of you have probably seen that video before, so I'm not going to belabor the point. There are 4 streams. I'll briefly talk about each of them. And there's a core training and there's a research component. So of course, we want to equip you with some solid understanding of underlying computing and data analysis technologies and methodologies. We want you to bridge this gap between application domains, big data challenges, and high-performance computing. And we'd like to make you aware of the societal, economical, and ethical responsibilities that this work entails. So as mentioned, there's astrophysics, financial mathematics, Earth and Environmental Sciences, and Computer Vision and Robotics. This is the first year that Computer Vision and Robotics has run, and it's been extremely successful. I'm quite proud of this stream. We'll start with astrophysics. So of course, astrophysics concerns astrophysical domain, right? Stellar structure and evolution, stellar populations, stellar dynamics, galaxy clusters, the Milky Way cosmology writ large. There's quite a bit of physics in this stream. There's financial mathematics. So this is primarily concerned with the mathematics of finance, of markets, of probability and statistics, and indeed some partial differential equations. We really do need to emphasize that this stream requires some significant sophistication in mathematics coming in, because it's very difficult to learn both the computational and the mathematical aspects simultaneously. You really need to come in understanding the math. There's the Earth and Environment stream, which includes spatial information systems. You've probably heard of GIS if you are interested in this field, as well as remotely sensed data. There's a lot of forward and inverse modeling to interpret environmental data, and a lot of statistical modeling. And of course, computer vision and robotics. This includes supervised and unsupervised deep machine learning techniques, automated scene understanding from various sensor payloads, and robotic guidance, planning, and control. So that's all good. As an overview, the course is split into 3 streams. So in term 1, that's this column here, you'll have some training in professional skills, as well as your core 1 modules, and you will take some modules in your specialization. In term 2, you'll continue with professional skills and your specialization, and you'll be able to select some core 2 modules. And then term 3 is dedicated to your research project. So that's fully a third of your course. It's very important. So that's happening right now for the current cohort. We'll skip the term overview because I think most of you have seen this before. And I do want to note that in MISCADA, all of the assessment is coursework. So you will be given an assignment, some sort of small project, and then you'll hand in some documents, either code or a report, or give a presentation afterwards. This is quite nice because it means that you, with a single exception, you wouldn't have an exam. There's one module that has an exam. So like the video mentioned, a lot of our students go on to do PhD programs or go and work in R&D divisions and companies. Several have gone on to work in national labs. So there's really a great deal of opportunities for future employment coming out of this program. I think we have a really good track record in that regard. Now, Durham specifically, the video mentioned, it's a world top 100 university, 17 distinctive colleges. It's the 3rd oldest university in England, with a strong international community, strong industrial links, and excellent employability. We're in a historic city. It's pretty easy to get around. The city itself is pretty walkable, and we're very well connected to other areas in the UK. You can get to Newcastle in 12 minutes, which is really fantastic. It's safe, beautiful, and historic. It's a World Heritage Site. It's very walkable. There's plenty of countryside. I'm going to skip this video. And there's a great deal of support here in Durham, including for immigration, healthcare, finance, student well-being. We have a really solid well-being group here at the university. Counseling, there's a strong EDI team, and chaplaincy and faith teams. Okay, so you are maybe familiar with the entry requirements for MISCADA. This is a 3 or 4 year bachelor's degree with a 60% and above in physics, or a subject with basic physics courses. So something like computer science, mathematics, earth sciences, engineering, or any natural science with a strong quantitative element. There are, for the IELTS, 7 bands or equivalent. There's a minimum speaking requirement of 6.5. And you are expected to have some programming knowledge on a graduate level in both C and Python. In practice, you can use any compiled language and Python. Everybody needs to know Python these days. For the financial technology pathway in particular, we strongly recommend a background in mathematics. Okay, so you are maybe familiar with the application process. Feel free to email Anna or myself, or you can email the MISCADA director mailbox if you have any questions. Now, I want to share with you a testimonial from one of our current students.
My name is Prerna Kotapalli. I am from the US and I'm studying the Master's in Scientific Computing and Data Analysis with a specialization in astrophysics. I was looking for a course that would combine astrophysics and scientific computing. This course obviously fits the bill perfectly. This is so that I can develop some of my computing skills before pursuing more research in astrophysics. The professors have been incredibly supportive and kind, very available with their time and willing to answer questions inside and outside of class. I'm applying to graduate schools and they've been giving me a lot of advice on my career and further education and have provided letters of recommendation for me as well. My top piece of advice would be, once you get to Durham, engage in all of the societies that are here. Take the opportunity to meet the very interesting people that come from everywhere to study here.
Okay, so that's one of our current students, PK. She's very good. We're really glad that she agreed to do a bit of a testimonial for us. Now, this is an academic taster session, so the bulk of the time I'm going to talk about some of the content you'll see in this course. So if I just share a different window, here we are. Okay, so I'm the deputy director for MISCADA, and I teach on MISCADA. In fact, I teach one of the core modules in term 1. I teach the high performance computing submodule. And this is a little bit of a taster from that first lecture in that module. So this is going to be an introduction to high performance computing. Now, before I begin the slides, I just want to ask if there are any questions about what we've seen so far. You can put them in the chat or use the Q&A feature. Okay, it doesn't appear that there are. So I'll just go ahead with a taster lecture. Okay, so this is Introduction to High Performance Computing, Introduction to Parallelism. So this is the first lecture, so we're not going to get too technical today. Now, I typically do a little bit of a quiz at the beginning of each section just to give people an opportunity to provide feedback and keep track of how well people are keeping up with the content. And this is usually how it's presented. You'll have a QR code or a link to the quiz. It's not active right now. I'm not going to quiz you in a taster session. And it'll contain it, and then I'll go over an outline of the overview of the lecture. So the lecture concept, the idea of no free lunch, which we'll get to in a minute, and then I'll talk about Flynn's taxonomy, some speed-up laws, and parallelization concepts that we'll use throughout that module. I also like to begin the first session with a disclaimer. You need C for this course. Now, nowadays, quite a bit of high-performance computing is done in Python, but in order to have really good control and understanding of the parallelization concepts, you need C. It's a standard. We're going to use it in this module. So you'll see code throughout these slides and throughout the course that looks a bit like this. You might recognize this include statement. That's for standard IO. And then int main. So main is a function that returns an int. And all it does is printf hello world and then return 0. So this is a very, very simple C program. Now, in the module itself, there are 3 didactic pillars. There's coursework, there's a lecture, and there's exercises. I'll talk a bit about an example exercise in a bit, but we'll just talk about the lecture for now. And throughout the high-performance computing course, I'm not expecting you to bring your own high-performance computing. We're going to use the resources here in Durham. So all the experiments, the source code will be available online. It's all plain C or C++. There's, in fact, very little C++. It's strongly recommended that you use a Unix environment. So that's Linux or even Mac OS. Windows has some quirks that makes it a bit annoying to use, but nowadays you can use the Windows subsystem for Linux, and that works quite well in practice. And as part of this module, you'll be given access to Hamilton or Cosma, which is 2 of the 6 or so clusters available here at Durham. Hamilton is the one that I tend to use for the course because it's very well supported, but Cosma is really useful for larger research projects. I also specify some tools, so I'll use GCC in the course because it's generic, it works everywhere. There's OpenMPI, which is already on Hamilton, but you can also install it locally if you want to do testing. And you can use the Intel Parallel Studio, which is free for students if you like. Now, you've probably all heard of Moore's Law. You've maybe heard a slightly different version of it. Now, Moore's Law, in fact, is just a statement about the complexity for minimum component costs in CPUs. Has increased at a rate of roughly a factor of 2 per year. So that means for a fixed cost CPU in 1 year, and the next year, the one from the following year will be about twice as complex. It'll have twice as many components. Now, Moore was co-founder of Intel and also R&D director of Fairchild Semiconductor. So he has a great deal of experience. He knows what he's talking about. This comes from an article that he published in Electronics magazine in 1965 called Cramming More Components onto Integrated Circuits. He's also responsible for Intel's tick-tock policy. You may have heard of this. It is a change of microarchitecture rather than a die shrink every other year. And then Carver Mead of Caltech coined the term Moore's Law in 1975. It's about chip complexity. It's not about speed or computational power. Now, you can just verify this. In fact, there's a very nice Wikipedia article called Transistor Count, which validates this assertion. So if you plot the number of transistors versus the year for a bunch of CPUs over time, you get this very nice log linear trend. And if you fit a line to this, you can find out that it doubles approximately every 2 years. So Moore's Law is a statement on transistor count or hardware complexity for fixed price. It's used to translate directly into performance for decades. If we study the performance growth for the biggest machines in the world, we'll see that the picture is pretty clear. You may have heard of the top 500 if you're interested in high performance computing. This is a list of the top 500 supercomputers in the world, at least the publicly available ones. So it's just top500.org, and it's collated by supercomputing and the international supercomputing groups. Moore's law seems to continue to hold for speed too. So if we look at the number one, which is these orange triangles, you get this nice linear trend over time. If you look at number 500, you get something a bit like a linear trend. There's maybe something happening more recently. If we look closely, this is data collected by a number of people, most recently by Carl Rupp. If you look at the number of transistors in thousands, this Moore's law trend holds quite well, even very recently. But something interesting is happening with single-threaded performance. It continues to follow, or rather, about 40 years ago, it was following this linear trend with transistors quite closely, but more recently, it's starting to level off. So that's a statement about the actual throughput in a single core over the years. If we look at the frequency, it's even more complicated. So not only did it sort of peak around 2008, it decreased slightly in more recent years. And if we look at the power, things converged for a while, but now they're starting to spread out again. So this year, this would be 2023, we have 3 data points, and they're actually quite a bit different from each other. Now, the important thing to note is that the number of logical cores was 1 up until about 2005. You had very few machines that had more than 1 core in the CPU prior to 2006. And then they started to slowly grow. So you go from 1 to 2 to 4 to 8. And now it's not unreasonable to have something with a couple of hundred cores in a single server. On your personal laptop, probably not several hundred cores, but I mean, maybe, I don't know. So the number of cores has increased significantly in the past 15, 20 years. The number of transistors has been pretty steadily growing, but the single-threaded performance has been leveling off. So that means that the actual performance improvement in recent years is due entirely to the number of logical cores in the CPU. Now there's something quite significant that's not in this plot. You've maybe heard of general purpose GPU computing, or using a GPU to do highly parallel computing tasks. That's obviously not included in this data, but it has its own sort of interesting narrative that we can maybe talk about if someone has questions. So the free lunch, so back in the day, if you wanted a faster machine, you just increased the frequency. So you fed it more power, you let it clock higher, you tried to get rid of all the heat that was generated. It was kind of a free lunch. You didn't have to think too hard. That's single-threaded performance. The free lunch is over. So the increase in performance stems from concurrency, which is supported by the increase in the number of logical cores. So it's really important that you actually learn how to exploit concurrency. And indeed, how to exploit parallel computing. Now, we really rely on performance improvements. So there are 3 classic objectives of high-performance computing or computational science. There's throughput and efficiency. So if you can get your results faster, that reduces cost. It means that these scientists or engineers can do more experiments in a given time frame or study more parameters. This is especially relevant for a field called uncertainty quantification, which is very interesting and extremely popular, and I think in the future going to be even more important. There's also a question of response time. So there are things that are urgent to compute, like tsunami predictions or things with medical applications. So I work on cardiac problems. So if we have a patient who is experiencing chest pain, how do we run a computation that can tell us whether that is something that needs immediate treatment or something that will sort of go away on its own? This can also be something that's like interactive. So something which is steered by a user, which can also be extremely productive. And then the other objective is problem size, right? We solve problems. If you think of like astrophysics in particular, we try to resolve galactic scale things and also planetary things. And doing that at the same time can be quite expensive. We've invented a number of very interesting computational techniques in order to address that sort of problem. Sometimes new insight really comes from achieving never seen before resolution into scales in space or time or both. So, throughput and efficiency, response time, problem size, these are all driving factors in the solution of these problems. So if a single core is not getting much faster anymore, then we have to squeeze more of them into one computer. How do we actually use a computer with many cores? We have to write parallel codes. If computers become more parallel, we have to write more parallel codes to exploit that. Okay, so when we're talking about parallel computers, we have to talk about Michael J. Flynn. So he was born in 1934 in New York City. He's Stanford University emeritus. The paper that we are going to talk about a bit today is called Some Computer Organizations and Their Effectiveness, which was published by IEEE. So this is Flynn's taxonomy, which you may have heard of before. This is just a broad overview. Flynn's taxonomy concerns itself with streams. On the one hand, you have an instruction stream, which is a sequence of commands. This is a top-down classification. Or data streams, so a sequence of data that's coming in that needs to be processed with these instructions. So the data streams are going to be left-right. The combination of data stream and instruction stream, if there are two options for each, yields 4 combinations. So on the top here, we have instruction streams. We have a single stream or multiple. And on the left, we have data streams, which we have single or multiple. And if you combine each of these, you get one of these 4-letter acronyms, which I'll talk about briefly. So the first is single instruction, single data, SISD, or multiple instruction, single data, MISD, or single instruction, multiple data, SIMD or SIMD, and the general case, multiple instruction, multiple data, or MIMD. Now, SISD is, I think, how most of us think about computing. You have one thing that's doing the work. You have one activity at a time. So if we want to do C is equal to A plus B, and A, B, and C are vectors and Rn. So that means A is a vector with n elements, B is a vector with n elements, C is a vector with n elements. How do we fill the vector C based on the values in A and B? So with SISD, the runtime requires 2 loads. So you load an element from A and an element from B. You do an addition, and then you store it in C, and you have to do that n times. Now, usually load, add, and store require multiple cycles. This depends on your hardware and the environment, but we're not going to worry about that. So the idea is that 4 into I equals 0, I less than n. I increments by 1. We load AI, we load BI, we add them together, and then we store it in C. So this is pseudocode for what's actually happening behind the scenes for this computation. Like I said, this is how most people think about computing. If you write a program, how do you actually reason about it? You think of a sequence of operations completing in a particular order without details of data locality or hardware. Now, if you have multiple instructions and multiple data, so you have, say, 2 different CPU cores or multiple processors, you can do the same computation, but you can split it up for each processor. So for 2 cores, you can have the first one load AI, load BI, add and store, only up to n over 2. And then for processor 2, it does the same thing, but for the range n over 2 to n. So this computation should complete twice as fast as the previous one, because you have 2 processors doing completely independent tasks. They should be done in half the time of a single processor doing the whole thing. So we often think about MIMD hardware as multiple SISD computers working collaboratively on some subproblem. Now, MIMD typically describes many processors working on their data independently. So we have that length n array for A, B, and C. If we split it in 2, then those 2 halves are handled independently on each processor. This is typically thought of as single program multiple data. It's not a hardware type, but it's a programming paradigm. It's a way to actually write a program that executes in parallel. So all chips run the same instruction stream, but they might process different steps at the same time, which is nice because there's no synchronization. Throughout the module, you'll see that synchronization can be a persistent issue in achieving high performance. But MIMD is a description of hardware. It doesn't say that we have to run the same program or algorithm everywhere. So we've covered 2 of the classification areas, SISD, which is sort of a von Neumann computer principle, as classic single processors with 1 ALU, 1 logic unit, 1 instruction on 1 piece of data at a time, or MIMD, which is a classic way to think about multi-core or parallel computers as multiple SISD computers with asynchronous execution of several instruction streams, though it might be copies of the same program, and that might work on the same data space, but the processors do not automatically have to synchronize. But there are 2 others, right? There are 4, we've covered 2, so there are 2 more. How about SIMD? So that's single instruction multiple data. The ALU still does 1 activity at a time, right? It's only getting a single instruction. But the registers, the actual pieces of memory on the chip, hold more than 1 piece of data. So in this example, they're holding 2 pieces of data. And the arithmetics update both sets of data at the same time using that 1 instruction. So if we go back to C equals A plus B with A, B, and C and Rn, then at the runtime, we have 4 loads, 1 add, and then 2 stores. And that's done n over 2 times. So we're sort of jumping along A, B, and C to do more than 1 piece of work at a time. Now there's some details around load, add, and store. It can be slightly more expensive than in SIMD. SISD. And load and store can grab 2 pieces of data in 1 brush when they are stored next to each other. So you might have some pseudocode that looks a bit like this. So we have one processor, a single instruction, multiple data. So for I equals 0, I less than n, I now increments by your vector width. So that's little n. You can usually look that up for your hardware, your particular CPU. In practice, it's between 4 and 8, depending on your data type. And the idea is that you load AI through AI plus n, and you load BI through BI plus n. You do a vector addition, so not just an addition, a vector addition, and you store that vector addition output in CI through CI plus n. So the idea is if you have one processor, but with SIMD capabilities, you can speed things up considerably by having the processor handle the same instruction across a larger set of data. Now, SIMD operates at a lower level of hardware parallelism than a CPU core, right? It's happening on a single processor. So it's operating at the level of execution units like the ALU and FPU. So that's arbitrary logic unit and floating point unit. So the ALU will typically be responsible for integer math, and the FPU will typically be responsible for floating point math. Or at least you can think about it for today's purposes. Likewise, it is frequently preferable to implement SIMD parallelism automatically using compiler optimization. So the nice thing about SIMD is, especially in C, you don't have to write it yourself. It would be kind of annoying if we had to carefully consider how big n should be and load all of these variables manually and remember to do a vector addition. The nice thing is, if you ask nicely, the compiler will generate this code for you based on original, simple, single instruction, single data code. So that's quite nice. This is called vectorization. So either you or the compiler rewrite your implementation to make it work with small or tiny vectors. The extent, like I said, extending to 4 or 8 is pretty straightforward. Going to longer vector lengths can be actually quite involved, but usually not too bad. This technique is called vectorization or vector computing, and it requires some hardware support. So you need large registers holding multiple logical registers in order for it to work. So you need somewhere on the CPU for that load of AI, AI plus 1, AI plus 2, and so on to actually go into. You have maybe heard about SSC, that's streaming SIMD instruction. That originally supported just 4 floats. So if you think about it in terms of doubles, which is like your standard floating point double type, standard floating point data type these days, that would just mean 2 doubles, or it's 16 bytes, or 8 16-bit shorts, 4 32-bit integers, 2 64-bit integers, or 1 128-bit integer. So you can also use SIMD to slow down your computation if you need something with much higher precision. Now, SIMD has been around for quite some time. It's really only been practical for the past 25 years or so. More recently, you may have heard of AVX 512. That's a fairly recent innovation. Intel implemented it a couple of years ago, and it had some problems. So they've kind of stopped using it on their consumer CPUs. But AMD is using it now. So for example, the machine to my left, I guess stage right, has AVX 512, and it's really, really great. Yes, okay. So AVX doubled the number of registers. It let multiple cores share registers. You can store results in the third register, so you don't have to overwrite things as you go along. And you can gather and scatter operations with fused multiply add, which again, really, really great. Now, there's the fourth classification. SIMD, synchronous execution of a single instruction across multiple inputs. In practice, this means using tiny vectors, 4, maybe 8 values, and doing things simultaneously, which in principle means you can speed things up by a factor of 4 or 8 on a single core, which is, sometimes that's all you need. Now, the final classification is multiple instruction single data. This is quite different. This means I have multiple instructions being fed to my CPU to act on a single data stream. One archetypal example is pipelining, which you maybe know about if you're interested in CPU design. It is coming back into being really important, especially on ARM machines, because with a reduced instruction set, you can be a bit wider with how many instructions are fed in. So that can help speed things up or make things more efficient. So you'll find that a lot of the modern ARM machines are actually much more efficient than a lot of x86 CPUs. We're not really going to talk about it here. It's a single data and multiple instructions. It has kind of limited utility in that sense. There is a potentially really interesting and important use case. If anyone wants to venture a guess, feel free to put it in the chat. No? Okay, so a really important use case for MISD is space exploration. So if you think about a satellite as a computer with a big camera and some power sails being sent into the great unknown, it's experiencing, the vacuum of space, it's experiencing the solar wind. It's very important because it's a really big financial investment that it works correctly. So if you're giving it multiple instructions and one data stream, that can be quite useful because it should produce outputs that are robust if something happens. This is something that was used by NASA on the space shuttle however many years ago. So it's still important, but it's sort of less interesting from the high performance computing perspective. Okay, now in terms of the lessons learned or the insights that we get from Flynn's taxonomy, all three paradigms are often combined. So with Haswell, this is actually from quite a while ago. This is 22 nanometers, so this was like a decade or so ago. It combines SISD, right? Because you have a single core here, it might be doing its own thing. It has MIMD, has multiple cores. They can work together with this shared L3 cache in order to solve a larger problem. And it has SIMD. So not only do each of these cores have their own SIMD capabilities, but the processor graphics, the integrated graphics, is effectively just a SIMD processor. And it's kind of additionally specified to graphics problems. So in almost every computer, there's more than one flavor of hardware parallelism. There's more than one parallelization approach. And indeed in MIMD, you have all these different subtypes. So you can get shared versus distributed memory, races versus data inconsistency problems, synchronization versus explicit data exchange. And all of these will be covered in the HPC module. Okay. I think what I will do is leave it there. The next thing I would talk about is Jean Amdahl and Amdahl's law, which is about parallel scaling. But I'd be more interested to answer any questions that anybody has. Ooh, I can actually talk about the exercises. Let me share that. Okay. So in the high performance computing module, I split things up. We have a lecture and we have a workshop. We have 2 of these each every week. Now, you've seen a bit of the lecture, but I want to talk a bit about the exercises because I think the exercises are really good for helping you develop skill. So this is one of the early exercises. This is about array timing with OpenMP. If you don't know what OpenMP is, don't worry about it for now. Now in programs, when you lay out your data, how that data is laid out in memory, like in the physical memory of your machine, can be very important, especially for efficiency, for timing. C has column ordering. So when you lay out, say, a multi-dimensional array, it lays it out by column. Sorry, it lays it out by each row and then each column. So if we have 3 arrays, A, B, and C, and each one is an array that is 3D, and each dimension has n length, we can ask how long it takes to add each element in A and B and store it in C. So this is kind of a silly computation, right? It's pretty trivial. The computation itself doesn't change if you change how you traverse each array, but you're doing it over n cubed elements. So for even n relatively small, this can be quite a few elements to actually iterate over. In fact, I include this warning here. If you take n much larger than 64, then you will likely hit stack limit size. So that's a limit on how large you can make an array in the stack, which will segfault. That's usually an indication that something's not correct, but in this case, it's just the operating system trying to save you from yourself. And you can use this command, ulimit -s, so that's the user limit for the stack, and set it to unlimited. Now these exercises vary in difficulty quite a bit. Some of them take 15 minutes. Some of them take a few hours to really understand. This is one of the easy ones. So I include this function here for timing. The idea being, if instead you had 2D arrays, A, B, and C, and you wanted to time how long it took to add each element of A and B and store it in C, you could follow this sort of format. So in the exercises, you'll typically have some demonstration code or code to build off of so that you're not building everything from scratch each time. And these exercises will typically have blocks like these where we ask questions. So how did you implement things? How many loop orderings are possible? What is the timing that you get on your machine or on the cluster, more likely? If you make n and m command line arguments, so that's the size of the arrays and how many times you do the computation to check. What is the timings? Is the ranking different on Hamilton 8 than on your machine? How do you parallelize things? Can you parallelize the code using a particular pragma? So this comes from OpenMP, which is something we'll get to in the course. How many threads can be used? and some additional options. Now, a lot of the exercises also have challenges. So something that's a bit more difficult to do, something more interesting, usually, but for which I don't have a complete solution for you. But you can think about it, work on it. It might be interesting for you to try it on your own. And then each of these exercises will have a set of aims for you to understand. So in this one, it's array access performance for multi-dimensional arrays in C, an introduction to parallel loops with OpenMP, an introduction to the collapse clause in OpenMP, and an introduction to some basic numerical computing options, in particular this challenge here, where you try to calculate the mean and variance of something on the fly. Now, if you'll bear with me for a second. So I just rebuilt this document, and now you can see that there is a solution for the exercise. So on my machine, in fact, the machine I'm using right now, there are some results for n equals 64 and m equals 1024. I found that IJK is the fastest. It's about 60 milliseconds. This is, well, this is perhaps a little surprising because in C, it's the first access, which is memory contiguous, so the fastest to traverse. And the reverse, so if IJK is the fastest, then the reverse is KJI, which is close to the slowest. It's not quite the slowest, but it's pretty close. Now, I rather like the Julia language. I don't know if anybody here has heard of it, but for some of the exercises, I also do a comparison in Julia. And for this one, I did some comparison, and I found that it was quite a bit slower overall. So I think, oh, this one. This is the fastest time I got using Julia, which is KJI. Julia is row major order, so the opposite of C. So it's not surprising that KJI is the fastest for Julia, but it's much slower overall than C. It's about 4 times slower. So yes, okay, so there's solution. It's quite nice. There's a solution for the other part of the exercise. So these will typically include some programming effort, some mathematical effort, some understanding of the outputs that you're seeing. And what they're really there to do is to give you training for the coursework at the end of the course, which is meant to do to give you an opportunity to parallelize something and really think about how it should be implemented in parallel. Thank you all for coming to this session. I hope you enjoyed what you saw. Of course, if you have any questions, feel free to email me or the director, and we'll be happy to answer anything we can. Yeah, thank you very much. I hope to see many of you in high performance computing in the fall.